This is the Mandelbrot set, one of the most beautiful and remarkable discoveries in the entire history of mathematics. Yet it was discovered as recently as 1980. The invention of the silicon chip in the 1970s created a revolution in computers and communication, and hence transformed our way of life. We are now seeing another revolution, which is going to change our view of the universe and give us a better understanding of its working. I'm Arthur C. Clarke. I write science fact and science fiction. You may know my movie 2001: A Space Odyssey. I've seen some remarkable developments and inventions in my lifetime, but one of the most extraordinary is the Mandelbrot set and fractal geometry. This film will explore the fractal universe, and on our voyage of discovery, we'll be helped by Professor Ian Stewart of the Mathematics Institute, University of Warwick, and author of over 100 published scientific works. Dr. Michael Barnsley, former professor of mathematics at Georgia Institute of Technology, who received a $2.5 million government grant in 1991 to develop fractal image compression systems. Professor Stephen Hawking, the mathematician and cosmologist, and author of the best-selling book, A Brief History of Time. And finally, Dr. Benoit Mandelbrot, whose unorthodox mathematics led to the discovery of the Mandelbrot set and fractal geometry.
I first saw the Mandelbrot set somewhere in the mid-80s. I remember it quite clearly. We were at a mathematical conference on something totally different, and everyone went along to this exhibition because it was mathematical pictures. And there were these amazing coloured pictures on the wall, and I'd really not seen anything like this before. It's not easy to describe the Mandelbrot set visually. It looks like a man, it looks like a cat, it looks like a cactus, it looks like a cockroach. It's got little bits and pieces that remind us of almost anything that you can see out in the real world, particularly living things. So it has a character that reminds us of a lot of things, and yet it itself is unique and new.
The Mandelbrot set is real, an absolute thing, no question whatsoever. Any mathematician or any computer scientist or student in a school can study it and find the same, describe the same thing. It's a common experience. And so such things that can be magnified forever and have infinite precision do exist, but they're not touchable.
It's a geometrical shape, an icon, if you wish, which somehow embodies as an example a very important aspect of how the world works. Somebody recently actually called this set the thumbprint of God.
Now we'll begin our serious exploration of the Mandelbrot set, a voyage which, in fact, could last forever and ever, much longer than the lifetime of the universe. I have here the full set, about 6 inches across. Now, if I blow this up, I'll increase the magnification now 13 times, and you'll see more and more detail is appearing. And the interesting thing is you see mini Mandelbrots, replicas, almost identical, yet perhaps subtly different, of the original set. And I can go on doing this. Here's a magnification of more than 3,000 times. So the original picture, about 6 inches across, is now half a mile across. And no matter how much we magnified it, a million times, a billion times, until the original set was bigger than the entire universe, we would still see new patterns, new images emerging, because the frontier of the M set is infinitely complex. And when I say infinitely, I really mean that. Most people, when they say infinitely, they mean only rather big, but this is really infinity. What is so remarkable, in fact, astounding, about the Mandelbrot set is that although it's infinitely complex, it's based on incredibly simple principles, unlike almost everything in modern mathematics. In fact, anybody who can add and multiply can understand the principles on which it's based. You don't even have to subtract or divide, still less use logarithms or trigonometrical functions to comprehend how the Mandelbrot set is created. In fact, in principle, it could have been discovered any time in human history and not merely in 1980. But the problem is this: although it's only based on adding and multiplying, you have to carry out those operations millions, billions of times to create a complete set. And that's why it was not discovered until the era of modern computers. It was on the 1st of March, 1980, at IBM's Thomas J. Watson Research Center in upstate New York that Benoit Mandelbrot first glimpsed the M-set. The seeds of this discovery were, in fact, sown decades before the M-set was first seen. In Paris, in 1917, a mathematician called Gaston Julia published papers connected with so-called complex numbers. The results of his endeavors eventually became known as Julia sets, although Julia himself never saw a Julia set. He could only guess at them, and it wouldn't be until the advent of modern computers that Julia sets could be seen for the first time.
For me, the first step, almost a difficult mathematical problem, was to program it and see how it looked like. We started programming Julia sets of all kinds. It was extraordinarily great fun. And in particular, at one point, we became interested in Julia set of the simplest possible transformation. Z goes to Z squared plus C. So Z times Z plus C. I made many pictures of it. First of all, the first one was very rough. But the very rough picture, that was not the answer. Each rough picture asked a question, so I then made another picture, another picture, another picture. And then observations came up. For example, initially we had this Julia set as a big black blob, people call it a bug. And then when the bug became more precisely drawn, there was all kinds of junk around it. Now, the junk might have been anything. For example, part of the junk was just a very poor computer system we had. In fact, it was a miserable system. So what we did was to act like a naturalist, like somebody 18th century botanist or zoologist. You take a microscope and look closer to see what happens. So we looked at some of these little pieces of junk by magnifying the Mandelbrot set, and they vanished because they were just junk. And others did not vanish. So as we did it, something quite extraordinary came up, which is that if you magnify a small piece of the Mandelbrot set, that piece looks like Julia set itself. So the whole Julia set has a kind of say miniature version of itself in the Mandelbrot set. And after a few weeks, we had this very strong, overwhelming impression that this was a kind of big bear we have encountered. I think the most important implication is that from very simple formulas, you can get very complicated results. It's fundamental from viewpoint of the very base of science, because what is science? We have all this mess around us, things are totally incomprehensible, and then eventually, more or less rapidly, more or less hard to achieve, we find simple laws, simple formulas. In a way, a very simple formula, Newton's law, which is just also a few symbols, can, by hard work, explain the motion of planets around the sun and many, many other things to the 15th decimal. It's marvelous. A very simple formula explains all these very complicated things.
There's an interesting parallel with the equation that almost everybody is familiar with, the only equation almost everybody is familiar with, E equals mc squared, Albert Einstein's equation that says matter and energy are equivalent to each other. That was a very simple equation with very far-reaching consequences. And the equation for the Mandelbrot set is equally simple. Z equals Z squared plus C.
The letters in the Mandelbrot equation stand for numbers, unlike those in Einstein's equation where they stand for physical quantities, mass, velocity, energy. The Mandelbrot numbers are coordinates, positions on the plane, defining the location of a spot. Another difference from Einstein's equation, and a very important one, is this double arrow. It's a kind of two-way traffic sign. The numbers flow in both directions, constantly feeding back on themselves. This process of going round and round a loop is called iteration. It's rather like a dog chasing its own tail. The output of one operation becomes the input of the other, and so on and on and on. When the Mandelbrot equation is given a number representing a point, and that number is iterated through the equation, one of two things happen. Either the number gets bigger and bigger and shoots off to infinity, or it shrinks to zero. Depending on which happens, the computer then knows where to draw a boundary line. So what we get from this basic iteration is a kind of map, dividing this world into two distinct territories. Outside of it are all the numbers that have the freedom of infinity. Inside it, numbers that are prisoners, trapped and doomed to ultimate extinction.
Think of a computer screen. You're looking at each individual little element, each pixel of the screen. You pick one of these pixels, you apply this rule lots and lots of times, and either the pixel moves off and disappears completely from view, or it moves in towards a fixed point in the middle of the screen. And what you do is, you just want to distinguish between going off out to infinity or going into zero. So any point that moves into zero when you apply this rule, you colour that point black. And any point that goes off to infinity, what people tend to do is colour it all sorts of wonderful rainbow hues about how fast it goes away. The important bit's the black bit in the middle. That's all the stuff that doesn't escape when you keep applying this rule.
Now, the colours are completely arbitrary. They could be anything, but they are not meaningless. A very good analogy is the contour map, you'll see, of a mountain range, for example, where the contours are drawn and coloured, the areas are coloured. The highest areas might be coloured white, and brown, then green, and then if you went on into the sea, deeper and deeper blues, just to show where the various levels occur. So it's the same here. You can make the colours anything you like, but they do define the different areas of calculation. And you can change them and get the most gorgeous results. Just look at this. Now, you may think that the frontiers are moving, but there's no motion whatsoever. Only the colors are cycling, in or out. Nothing is moving.
When you get very, very fine to very, very small details, the variations can become of overwhelming complexity. So complex that no single picture can possibly give justice to them. It's impossible in a black and white or color picture to show how complicated it is. The only way is to use what we call the color cycle. That is, the colors change regularly, and each set of colors in a way reveals a different property of these variations, a different variation. So by having this color cycling, one reveals in a very, very strong fashion the extraordinary complexity of the set. If the whole set were represented at this scale, the end of the set will go so far as to go somewhere near the star Sirius. Very, very far, enormously big, for this very tiny speck. Yet in the middle of the speck, you see an exact replica of the whole.
One of the most striking facets of the Mandelbrot set is the internal consistency of the object. It all hangs together. And if you look at the boundary and zoom in, if you look in just the right place, what you see is baby Mandelbrot sets, perfect in every detail. They're just slightly bent compared to the real set. You can't even see that, but if you look closely, they are. And they're decorated by slightly different external features. And then by the same token, if you zoom into the boundary of those, you see baby Mandelbrot sets, the second generation. And inside those, the third generation. It goes on forever. And so you're seeing islands of order in a sea of chaos.
I'm sure it's occurred to you that the Mandelbrot set looks like some kind of strange insect. It certainly has an organic feeling about it. It's got warts all over it, and it's also quite hairy. If we go out along one of those hairs, we find something rather interesting. Now look what's happening. At the tip of each hair, it splits into two others, and so on. Each is splitting, going on indefinitely. This splitting up, this bifurcation, going off into apparently random directions quite abruptly, is typical of a class of mathematical entities called fractals. The Mandelbrot set is the most famous fractal.
The word fractal means any geometrical structure that has detail on all scales of magnification. No matter how big you make it, you still see extra new details you didn't see before. And the name was actually invented by Mandelbrot himself. He felt he had to have a name for this area he realized he was working in. And so he coined the term fractal because it conveys this feeling of fragmented, broken, fractional, irregular.
It took a long time for us to emerge and start to look out at the other part of the physical observable universe, not as narrow studied little entities, the scientist who studies the flea on the back of the flea on the back of the flea, but rather being able suddenly to look out at the totality of nature and then say, my goodness me, we've got nothing to describe this with. Clouds are not made with straight edges. Trees are not circles. They're not triangles. They're something very, very different indeed. But there's a continual kind of a pattern that I can see as I look at the edge of a rising cumulus cloud, one of those very, very wrinkly, coruscated clouds that has such fine structure in it. And you say, but there's no lines or circles there. The wonderful discovery has been that there's an extension of classical geometry, Euclidean geometry, which is called fractal geometry.
Fractals are shapes which we are extraordinarily used to in, how to say, our subconscious, ill-organized life. For example, everybody knows that if you take a map of Britain on a small school globe, you see a very simplified shape. Cornwall is just a kind of triangle, and Wales perhaps a little rectangle. You can't put the details on a small map. If you look at in a larger map, you add more detail. The closer you come, in a certain sense, imagine yourself like somebody coming on a rocket. From far away, you see very little. And the closer you come, the more detail you see. If we come very, very close, you begin to see rocks, and finally the idea of coastline disappears, because one doesn't know any longer where is land and where is water. So indeed was arose in my mind to put together a geometry based upon many known facts in mathematics, scattered facts in mathematics, many scattered facts in our experience, many scattered facts in the results of what scientists had done of various kinds, all kinds of putting together all these things and using them as bricks, if you will, of a new building, which is a new geometry, which is a geometry of shapes which are equally rough at all scales.
One of the revolutions in thought that's resulted from this discovery is the realization that nature deals not in smooth, continuous objects, as we always imagined, but more often in fractals. And I'd like to show you how she does this. Now I'm going to generate a fractal before your very eyes. What you see here is what's called the seed, and it's an appropriate word in this case. Those two lines represent the first generation of the formation of a geometrical figure. And the computer has been told to continue growing these lines, but changing the direction every so often and at different distances. Now that's a very simple set of instructions, but look what happens after they've been carried out for, say, 10 generations. The tree I showed here, and it does look very much like a tree in nature, is symmetrical because the two branches at the beginning were the same length, off in the same direction. But if we change the length of one branch and change the direction, look what happens. In a way, this is a more realistic tree than the first one, because in nature you seldom have perfect symmetry. Much more elaborate structures can be created by very similar rules. I'd like to emphasize that all these shapes or objects, whatever you call them, although they look real, are generated entirely in the computer by following out a few simple instructions and repeating them over and over again. This is the way in which nature creates things.
It's exactly like the DNA in a butterfly's egg. Somehow that unravels and unrolls to form the extraordinary and beautiful pattern on a butterfly's wing with its myriads of colors and form. Somehow it's hidden in that seed in the DNA, and not only that, but the wings themselves probably only occupy a relatively small part of the total DNA. They are, if you like, a little formula that is unraveled by the process of growth and deterministic following of rules to form this natural and beautiful thing.
Living creatures seem to be complicated structures produced from simple rules, simple laws of physics and chemistry. And a lot of the structure that you see in living creatures is organic but pattern structure. Leaves on trees, ferns particularly, things like that, have the same feature that the Mandelbrot set has of you look at little pieces of them and they have lots and lots of detail. And in fact, the little pieces look very similar sometimes to the whole thing. It's very tempting to compare the way a simple formula produces a complicated Mandelbrot set with the way very tiny things in nature produce complicated organisms. And there are certainly some similarities in that there is the same kind of unfolding of a process. The instructions are there, but not an actual description of the object.
Once you develop a fractal geometer's eye, you can't help but see them everywhere. Every single thing you see is one way or another described by reference either to itself or to something else in the picture you see. It's as though you're staring at a vast dictionary, but the dictionary words are bits of pictures, and the references, the definitions of the words are made with other bits of pictures. And so you stare at one picture. I look out in the garden and at the trees, and I see this set of relationships between the picture and other bits of the picture. Those relationships are no more nor less than the assertion, from my point of view, that what I'm seeing is fractals everywhere.
The discovery of fractal geometry changes completely the kind of patterns we can look for in nature. And that is a really fundamental change to the sort of things mathematicians and scientists can do. And that's got to have a big effect.
Fractal geometry is already being applied throughout the physical sciences as a way of describing data in a new way. And the dream is that a fractal geometer can describe a cloud as simply as an architect can describe a house. He can use his intricate, repeatable formulas, simple formulas, to describe these unimaginably complex and beautiful shapes, and then communicate them from me to another scientist, to you. Here's not my straight line, build it straight, but here's my ragged formula, but it's very simple. Go build it wild like this. Can sort of think that they might even be the sort of semaphore of nature, of the physical world, of how it tells itself what it's supposed to be.
Let's go back to the Mandelbrot set and look at some more of the strange flora and fauna of the Mandelbrot Zoo. There's a certain similarity between these shapes. You can recognize they're cousins of each other, and yet they're all different despite their similarity. There's an infinite variety here, just indeed as there is in the world of nature. We see shapes that remind us of elephants' trunks, tentacles of octopi, seahorses, compound insect eyes. There's some connection between the Mandelbrot set and the way nature operates. I'm looking at Saturn, one of the most beautiful objects in the sky. In fact, we've discovered quite recently that the beautiful rings of Saturn, which have intrigued astronomers for centuries, do illustrate some of the phenomena we've been discussing in the Mandelbrot set. As you go closer and closer to Saturn, you see more and more detail which no one had ever dreamed of before the space age opened and we were able to get close-ups of Saturn and its rings. It's not surprising that when we have so many examples of fractals and related phenomena here on this planet, there are even more in the heavens.
To me, just looking up at the Milky Way is staring at a fractal. It's got an extraordinary dotty character, and yet if you take a magnifying glass to it, that is a telescope, and you look at it ever closer, you find that there are hundreds and thousands more little dots where you thought there was almost none. So you get an immediate example of a structure that seems to go in and in and in with more and more detail.
I had the great privilege of having a discussion with the famous cosmologist Stephen Hawking when I passed through London recently. And I said to Dr. Hawking, the Mandelbrot set is infinite in detail. You can explore it forever and ever, zoom into it. The real universe, however, does seem to have limits. As you go down into the micro world, you get, of course, molecules, atoms, neutrons, and perhaps subatomic particles, quarks. But does the real universe go on forever? Is there a limit, a basement, unlike the Mandelbrot set?
In the case of the universe, there seems to be a limiting scale. It is called the Planck length, and it's about 1,000,000 billion times smaller than an inch. This means that there is a limit to how complex the universe can be. It also means that the universe could be described by a theory that is fairly simple, at least on scales of the Planck length. I just hope that we are smart enough to find it.
He thinks that there is a limit in the real universe. There's a small size below which nothing exists, called the Planck length, which is about 1,000,000,000,000,000,000 millionth of a centimeter, unimaginably small. But that is the fundamental unit of size, the sort of grittiness of the universe, nothing smaller than that. So perhaps the real universe does end there in smallness, but we're not sure. It may indeed go on forever, like the Mandelbrot set. We just don't know yet. I'm often asked, well, these pictures are all very pretty, but what's their practical value? And I'm tempted to answer in the famous words of Faraday, who once said, when someone asked him what use were these experiments playing with wires and magnets, what use is a newborn baby? Faraday is also supposed to have told the Prime Minister, one day, Mr. Prime Minister, you'll be able to tax it. And in fact, fractal geometry, the sort of things we've been demonstrating, has enormous commercial value.
I think the discovery of the Mandelbrot set and of fractals in general is very important. It's important at the moment on an intellectual level more than hardcore technological level. There are some applications, but it's not yet put an important new gadget into every home, whereas things like the silicon chip certainly have. So most mathematical developments are like this. The ideas must come first, and then you have to translate them into practical things. And you can already see the beginnings of that translation occurring.
No longer do you have to draw a straight line through your data to make science of it. You could actually draw some fractal curve through it, or measure some fractal dimension of the data and do science. So the first application is in terms of a better description of the physical observable world. There's a new branch of mathematics available to all scientists, and that application will stretch on through the centuries now as the primary tool for descriptive physical science.
Phenomena of great irregularity are very, very widespread in nature. In the study of what's called condensed matter, polymers, such physical problems, one finds shapes of extremely great complication. These shapes could not be examined as geometric shapes before because there was no language to describe them. One couldn't describe the shape. One could only say things indirectly about them, saying, if you make such and such measurement on them, you'll get such a result. But that is, in a certain sense, a shadow of the object. It's the effect the object had on a certain measurement procedure. But the object itself could not be described without the geometry. That's a very mundane example, but which is the tip of the iceberg of an enormous number of structures, which are indeed only describable in terms of fractal geometry.
So the primary application will be as a tool for science in its own right. Science and then engineering, and on through into the building of the next generation of devices and equipment that will follow from that in terms of the sort of application that we think of. You know, will there be a new type of, not computer, because before you understood about desktop computers, they weren't here, and one didn't imagine them. But there will be new devices, new extraordinary devices, based on the principles of fractal geometry that will emerge over the next centuries.
Suppose you were the owner of a television station or a satellite which could broadcast just one television program. And somebody came to you and said, with the same amount of power, you can broadcast not one, but 10 programs. What would that be worth to you? Obviously, it would multiply the value of your investment 10 times overnight. Well, that's the sort of thing that fractal geometry makes possible. Atlanta, Georgia, headquarters of Michael Barnsley's Iterated Systems. In 1991, Barnsley received a $2.5 million government grant to develop fractal image compression systems. Corporations such as Microsoft, Mitsubishi, Multicom, and Virgin now use Barnsley's image and data compression software.
One of the most exciting moments occurred when I discovered the collage theorem. We'd been trying to work out how you could control a certain class of dynamical systems to make pictures of leaves. Then, struggling with the question, it just dawned on me that it was very simple. You needed to form a collage, a covering of the object with copies of itself, smaller, shrunken copies, so that the whole object was tiled with copies of itself. It's a self-reference statement. It's as though you took instead you might take a triangle and cover it with little triangles. You might take a square and cover it with little squares. Well, the theorem said if you took a fern and covered it with little ferns, then you would have created a dynamical system or a formula for a fern. But if you tried to actually create a picture using the collage theorem, it took hundreds of hours of graduate student time working on the problem. And the holy grail at this point for us became the question of, could we find a way to tell a computer, just look at a picture, a digital picture, and automatically go ahead and find the fractal formula for it. The discovery of how to automatically calculate the collage for an arbitrary picture came to me in a dream. From the early days of doing mathematics, I used to have a recurrent nightmare, which was something to do with studying matrices. And they kind of remind one of perhaps an old-fashioned telephone switchboard. Well, in the dream what happened was there was thousands of holes and lots of wires connecting everywhere to everywhere. And it was always a sort of tense muddle between the switchboard with all the wires going everywhere, always in a horrible tangle, and somehow it represented a matrix. I'd had this nightmare many, many times over 20 years. Night of the anniversary of my father's death, 2 years after, suddenly I saw in the dream how you could straighten out the switchboard, how all the wires would become untangled and nicely connected, and how you would join all the wires from big blocks to little blocks in the grid. And I woke up in the morning, I knew I'd discovered it, that this was it. This was the total secret to fractal image compression. How to automatically look at a digital picture, these ones made of the low resolution input, like your eye receives, and how to turn it into A, a formula, and B, an entity of infinite resolution. So the goal is now to be able to capture this fire of Prometheus, if you like, this fractal wonder, put it in a box, and being able to make this available to everyone.
Using Michael Barnsley's system, we can now compress images so they require drastically fewer bits to store them. Now, whether you compress or expand an image depends on the same fractal principles, and Barnsley's theories have now become a commercial reality. Let's take a look at one of his programs. If we take a tiny piece of this image, which has been stored in digital form in the normal way, and blow it up, it becomes very pixelated, and they're huge pixels. Now, if we take this very coarse image and pass it through Barnsley's fractal analyzer, we can actually reconstruct the details of the original image. If we then put the two images side by side, the difference is startling. So, where has all this detail come from? Well, this fractal image is a prediction based on the digital data sampled at the original low resolution. And you can, of course, magnify this image just as much as you wish, because, like the M-set, it has infinite resolution.
What you see are fractal textures, fractal creations that mimic the missing data. They are, if you like, interpolations or predictions, but they're done using fractal geometry. What happens is the original data is modeled by a fractal formula, and then we're looking at that fractal at greater and greater detail.
We're all used to seeing, every night on TV, the satellite view of the Earth with clouds moving over continents, showing the formation of storms and so forth. Now, those weather satellites have been operating for decades. What is not so well known is that there are also satellites up there, so-called spy satellites or reconnaissance satellites, which produce images of the Earth, or at least points of particular interest to the military, with thousands of times the definition of the weather satellites. But this means they have to transmit tremendous amounts of data to the ground, far more information than the weather satellites. So therefore, data compression, the ability to squeeze images and send them and then expand them again on the ground, is of enormous importance to the military. And we can thank those satellites for the fact that World War III is not yet broken out, and hopefully never will break out. fractal geometry also has surprising applications in medicine. This is the blood circulatory system of the human body, and yet you'll recognize it. It is a kind of fractal. Now we can understand what is really happening when our blood circulates. Here is the most important fractal of all in the human body, a small portion of the incredibly complex wiring circuit of the brain. We may never understand how our brains work, but if we do, I suspect they'll depend on some application of fractal geometry. Why I think there may be some connection between the Mandelbrot set and the wiring of the brain is because when I close my eyes and press my fingers against my eyelids, I see these patterns. I'm sure you're all familiar with them. You also see them when anybody gives you a bang on the head. Well, sometimes these patterns echo some of the shapes of the Mandelbrot set. Also, I'm told, I have never tried the experiment myself, that when certain illegal chemicals are ingested, you experience visual hallucinations strikingly similar to some of the patterns of the Mandelbrot set. Why do these strange patterns have such an appeal? Well, obviously they trigger some kind of resonance in the mind. And incidentally, there's an odd coincidence here. The name Mandelbrot and the word mandala for a religious symbol. I'm sure it's a pure coincidence, but indeed the Mandelbrot set does seem to contain an enormous number of mandalas or symbols. The Paisley pattern is one, and I'm sure there are many others. And in ecclesiastical design, such as stained glass windows, particularly in Islamic art, you find many echoes of the Mandelbrot set centuries before it was discovered.
I had this experience which many people repeated and told me about. I had this experience immediately that when I first saw them, I was the first person to see them. There was absolutely no way anybody could have seen before. Yet, after a few days or sometimes a few hours, a few minutes, it became almost familiar. I was finding features in it which I've seen somewhere. So where have I seen them? Well, first of all, certainly, as I said, in natural phenomena, but also perhaps in art. So one wonders, why is it so? We know the brain has some cells which handle its shapes, boundaries, and other cells which handle the colors. Does the brain have also cells which handle fractal complication? Well, we don't know. It's a purely hypothetical question. It's a tempting question, but we don't know anything about it.
Here's another strange resonance. This series of paintings was made in 1928 by a patient of Carl Gustav Jung, the co-founder of modern psychology. Jung would have been surprised and delighted to know that the computer revolution, whose beginning he just lived to see, would give new impetus to his theory of the collective unconscious. The idea that there is a well of consciousness compounded of primordial universal images that we all share, the substructure or background of awareness. The mind clearly finds resonances in the M set, but there are other wider implications too. This mathematics offers new insights into the way the universe works, how much in life is determined, and how much is due to chance.
When Isaac Newton came up with laws of motion and laws of gravity, the picture that emerged was of a clockwork universe. It was of a machine that ticked on a predetermined course. All we needed to know was where it was now and what it was doing now, and then you could predict the future forever. And there are two challenges to this. One is quantum mechanics, which says, in fact, there is irreducible chance built into the very fabric of the universe. And you can't actually say exactly what it's doing now. You can't say exactly what it's doing, ever. But the other is things that come out of the Mandelbrot set and related parts of mathematics, which is that even in a Newtonian world, in practice, you may not be able to predict the future. It can be deterministic in principle, but not in practice.
This is how God created a system which gave us free will. It's the most brilliant maneuver in the universe, to create something in which everything is free. How could you do that?
Albert Einstein refused to accept the idea of a dice-playing deity. He wrote a letter to Max Born in which he said, "You believe in a God who plays dice, and I in complete law and order." So he obviously felt that chance and deterministic laws were not compatible, and he preferred the deterministic laws. Now, what the Mandelbrot set and chaos and related things have done for us is to show that you can have both at the same time. So it's not whether God plays dice that matters, it's how God plays dice.
I can tell you, exploring this set, I certainly never had the feeling of invention. I had never the feeling that my imagination was rich enough to invent all these extraordinary things. I was discovering them. They were there, even though nobody had seen them before. It's marvelous. A very simple formula explains all these very complicated things. So the goal of science is starting with mess to explain by a simple formula. That's the kind of dream of science. And in this case, the dream is implemented in a fantastic fashion.
Often when I'm looking at my computer screen and watching the beautiful images unfolding, I'm reminded of Keats's famous lines, "Charmed magic casements opening on the foam of perilous seas in fairy lands forlorn." The Mandelbrot set is indeed one of the most astonishing discoveries in the entire history of mathematics. Who could have dreamed that such an incredibly simple equation could have generated images of literally infinite complexity? We've all read stories about maps that revealed the location of some hidden treasure. Well, in this case, the map is the treasure.